So students, in this lecture we will learn how to make shear force and bending moment diagrams for different types of beams. So basically shear forces and bending moments are the internal forces and moments which are present in a beam. So we will learn how to compute the shear forces at different points and the bending moments also of any beam. So first of all, we will learn about the sign conventions that we will take for this part. So there are two types of sign conventions. First is for external forces and external moments, and the other sign convention is for internal forces and internal moments. So the external forces and moments sign convention we will be using when we are calculating the reactions. So what are external forces and moments? So let us take example of a beam having these two loads, UDL and point load. So here the external loads are the reactions present in the beam and these external forces, and the external moments are the moments due to these forces. So what sign conventions we take for such cases is that for external forces we take upward sign to be positive and downward sign to be negative, right? And this force to be positive and this force to be negative. Generally we do not consider these forces in beams, but still we might use these sign conventions. Now for external moments, the sign convention which we use is clockwise is positive and anti-clockwise is negative. So this is for external forces. Now comes the internal forces. So internal forces in any beam is the shear force, the normal forces, and the internal moments are the bending moments. So while we are calculating shear forces, how do we take the sign convention? So for that, let me cut a section in the beam. So there are two ways of solving the question. Either you see the section from towards left side, or you see in the right side of the section. So on the basis of the direction which we are moving, we have different sign conventions. So the sign conventions which we will be using is that if we are solving on the left hand side of the section, the upward forces are taken positive, and if we are solving on the right hand side of the section, downward forces are taken positive. Similarly, in the left hand side, downward is taken negative and upward is taken also negative. Now for the bending moments, the sign convention we consider is that all the clockwise moment in positive and anti-clockwise all the clockwise moment in the left hand side and all the anti-clockwise in the right hand side are taken positive, and anti-clockwise in left and clockwise in right are taken negative, right? So this is the sign convention which we will be using for solving the questions. So using these sign conventions, we will calculate shear forces and bending moments at different parts of different points of a beam. Then after that we will plot the shear force and bending moment diagrams. So these diagrams are basically the representation of all the forces in graphical form. So for joining the different points, values of different points, we use either a line or a curve, right? So it depends on the type of load and the equation which we get for solving. So whenever we are solving either the shear force or bending moment, we will get an equation in terms of x, where x is the distance of the point from where we are calculating the shear force, like if in this beam we are calculating shear force at this point, so x will be this distance or this distance depending on the direction which we are choosing. So x here will be, so the equation will come either in the form of x, or it will be come in terms of a constant or x square. So depend, or sometimes x cube also. So depending on the nature of the equation of the line, we draw the corresponding lines and curves. So for, so for this I have made this table here, which shows that if we have concentrated loads and when we are drawing the shear force diagram, so we join the points with a straight line. And if we are drawing the bending moment diagram, then we have to use inclined line. So basically the main difference is that when we are using point loads, the equation of bending moment will come in terms of x, because bending moment is force into distance, so this will be x. So we will get inclined line for this type of equation. Then if we are having UDL, then for shear forces we will get inclined line, because again here also we will get equation in terms of x. Here in for parabolic we will get equation in terms of x square, so bending moment diagram will be parabolic. Then for UVL, which is uniformly varying load, here we will get equation in form of x square and here in the form of x cube. So the corresponding lines and curves are parabolic and cubic curve. So these are the different lines and curves which we will be using. So let's start with the first question. So in this question we have a beam which is supported at A and D, and DE portion is like a overhang because E is not supported. So in this beam we have one point load, one UDL, one UVL and one inclined load. So this question will cover almost all types of loads. So how do we start? The first step for calculating the shear forces is determination of reactions at the various supports. So in this beam we will have these reactions VA and VD, right? Here we will have another reaction HA also, because this is a hinge support. So first step is to calculate these reactions. So for calculation of reactions we use different equations of equilibrium, and the sign conventions which we will be using here will be for the external forces and moments. So we will take upward forces positive, downward negative, clockwise movements positive and anti-clockwise negative. So first we will use the equation sigma m. You can use any point, so I am using sigma m a is equal to md, ma is equal to 0. So this is the equation of equilibrium, showing that the moments of all the forces on the point A, the sum of the moments of all the forces about point A will be 0. So we will take the forces one by one. So now we will calculate the moments at A. So I will consider all the forces. So first I will start from E point. So before calculating the reactions, I will try to simplify the loads. So as you can see, we have one UVL, uniformly varying load, which is varying from 0 to 15 kilonewton per meter for a distance of 3 meters. So this is the DE portion of the beam. So whenever you are having a UVL in a beam, for the calculations you have converted it to point load. So for converting it to point loads, you just need to calculate the area of this triangle. So it will be half into 15 into 3. So now we have converted our uniformly varying load of 15 kilonewton per meter to a point load of 22.5 kilonewton, which will be acting at the CG of this triangle. And we know that for a triangle, if this is our triangle, then its CG will be, if this distance is, its height is h, then this will be h by 3. So this 22.5 kilonewton force will act at 3 by 3 meter, which is equal to 1 meter from D point, right? So now we have got converted the UVL to a 22.5 kilonewton load, right? So we will be using this. Similarly, you can convert the UDL also. So the UDL is 10 kilonewton per meter acting on CD portion of up to a length of 4 meter. So this will be 10 into 4, 40 kilonewton acting at the center of CD. So this means acting at 2 meter from C, right? So now for solving, I will take these forces. So here I will take 22.5 kilonewton force, and this is 1 meter, acting at 1 meter, right? This hole is 3 meters. And this is 40 kilonewton force. So this is also acting at 2 meter from C also and D also. So, okay, now another thing is that we have load point. So for inclined load, we have to resolve these. So I will resolve it into two components, 10 sine 40 and 10 cos 40. But we will be using only this vertical component for the calculations. So starting from E point, I will calculate the moments. So moment due to this vertical component at point E will be 10 sine 40 degree into this whole distance, which is 2 plus 2 4, 4 plus 4 8, 8 plus 3 11, and the moment will be clockwise. Will have a clockwise moment at A, and we are taking clockwise to be positive, right? So this will be positive. Then similarly I will take the next force, which is 22.5. So it will be 22.5 into distance between this point, which is the point of application of this force, and A is 1 plus 4 5 and 5 plus 4 9 meters. Then we have VD force. So moment due to VD will be counterclockwise because this is upward. So VD into 4 plus 4 8, right? Then we have a UDL. UDL will be also, moment due to UDL will also be clockwise. So 40 into, this is 2 plus 2 plus 2, which is 6, then 30 into 2, and moment due to VA and HA at point A will be 0. So solving this, we will get the value of VD, right? Then using the equation sigma Fy is equal to 0, we will get VA. Applying Fy is equal to 0 plus VD, because these two are upward forces. So for upward we are taking positive. VA plus VD minus 30 minus 40 minus 22.5 minus 10 sine 40. So we will get VA plus VD equation, which is this, right? So VD we had calculated by solving this above equation. So substituting it here, we get VA is equal to 27.28 27.27 kilonewton. Okay, so now we have calculated the reactions, and the third reaction I will solve it here. Sigma Fx is equal to 0. By applying this equation, we will have HA is equal to 0, because, okay, not 0 but HA there is a one horizontal force which is this 10 cos 40. So HA minus 10 cos 40 will be 0. So HA we will get 10 cos 40, but we won't be using this anywhere in our question, in this question. So now after we have calculated the reactions, the next step is calculation of shear forces. So I will first show the reactions which I have calculated. VA is 27.27 and VD is 71.65 kilonewton, right? And this is 10 sine 40, 22.5. Okay, so now to calculate shear forces, what we will do is, it's up to us. We can start from this direction to this or from E towards A, right? So any option will give you the same result. So I will be moving from A towards E. So first I will calculate the shear force at A, right? So for calculating shear force at A, I will draw a section just at the left side of A and look in the back side of this section, right? In the in the backward direction. So shear force is basically the summation of all the forces acting in the beam. So at this section we will just sum all the forces acting on its left hand side. So there is only one force acting here, it is 27.27 kilonewton, and the sign convention which we are using is that upward forces in left and downward in right are taken positive and vice versa. So as we are looking on the left hand side and the force is upward, so this will be positive. We will move to B point. So I will calculate shear force at B. And just to make a habit, always take section on both the sides of a midpoint of the points in the span of the beam. Like I am taking B point and I am taking one section just at the left and then I will take just at the right. Its significance we will come to know later on while we are solving different questions. So it is easier to visualize our beam like this. So when I am calculating shear force at B, just left, so I'm taking just left. So again, when we look at the back side of this section, then we have only one force which is 27.27, and so this will remain same, right? So at the left there will be no change. But when I'm taking the section at just right side of the point B, so now I'm considering this section just at the right of the B. Now I look at uh, look in the left direction of this section, then I have one 27.27 force and another 30 kilonewton force which is acting in downward direction. So 27.27 is upward in left hand side, we will take it positive, and 30 kilonewton is downward in left hand side, we will take it to be negative. So plus 27.27 minus 30 will give us the shear force as minus 2.72 kilonewton, right? Then I will take section at C again on left and then right. So when I am taking section at the left, then there is no change because we have only two forces. So we will get the same value, which is minus 2.72 kilonewton. So this is the same value at B because there is no change between B and C, right? Then when I'm looking at taking the section as just right of C, then also if I look at the back, there are only two forces, this and this. So this will be same as the shear force at B. So again this will be also minus 2.72 kilonewton, right? I'm just writing these again and again just to make it a habit so that you always consider sections on both sides. But actually when we are having same values, you don't need to write again and again. You can just write once that this will be same, right? But for more clarity, I'm writing it like this. Then I will take section at D at left hand side, right? So now I'm taking section just left. Okay, so when I'm taking section at just left of D, so comparing this section with the previous point, which is C, so up to C we have considered two forces. Now there another force is coming in picture here in the portion CD, which is the downward 10 kilonewton per meter force, which is basically a UDL. So this the equation for so this will become, so considering all the values, so either you can just write minus 2.72 because we have already calculated it up to point C, or you can write each value again. So any way you can work. So 27.27 minus 30 and another downward force of minus 40 because 10 into 4. So this will give us a value of minus 42.72 kilonewton at D at just left. Then we will calculate shear force at D just right. Okay. So now I am taking section just at the right of this point D. So here. So compare it with the previous value. So up to this section that is just left of D, we have taken three forces 27.27, 30 and 40, right? But now when I have moved towards right, there is another force which is 71.65, which is a reaction, and it is acting on the upward side on left hand side. So we will take it to be positive, right? So 27.27 minus 30 minus 40 plus 71.65. So we will get 28.93 kilonewton force in positive sign, right? Then we will calculate shear force at E point. Okay, so we will take this section here and look on the left hand side. So what we will see all the previous forces plus there is this UVL of 22.5 kilonewton acting now. So shear force at E will be all the summation of all the previous forces, which is, so either you can write again all these values, but now I am writing only this cumulative value up to point D. There is no difference. Okay, this is just for explanation, but you can take the last section, the value of the previous section which you have taken, so 28.93, and this force is again downward, so minus 22.5. So we will get the shear force value as positive 6.43 kilonewton. Okay, so these are all the values which we get at the point these are all the values of shear forces in this beam starting from A towards E, right? Then the next step will be the calculation of bending moments. Okay, so again I have to show the reactions here. This is 10 sine 40. This is 22.5 acting at 1 meter distance. and this is 40 kilonewton acting at the center, right? Bending moments also, I will move from A towards E, or anyway we will see in which direction it will be easier. So first I am calculating bending moment at A, right? So even without calculations, I can say that bending moment at A will be 0, as well as bending moment at E will be 0. You can calculate also, but you will get the same value because here E is at the end of the overhang. So we know that at the overhang end, the value of bending moment is 0, and A is the hinge support. So here also bending moment will be 0. So we will not consider these moments into calculations. Next, I will calculate bending moment at B. So I will take a section just at the left of B, right? So we will consider, so how we will calculate bending moment? Look at the left hand side of the section and calculate all summation of all the moments on this section, right? So there is only one force acting here, which is 27.27 into 2. Okay, so, and sign convention which we are taking is this, that clockwise movement in left and anti-clockwise movement in right are taken positive. So this will have a clockwise movement, so we will take it to be positive. So we are getting the value as 54.54 kilonewton meter, right? Next, calculation of moment at C. So now I will take section here. Now taking the moments of all the forces, summation of all the forces moments. So that would be 27.27 into 4, because the moment due to this reaction at this C, just at the left, the C point will be 22.27 into this 4, and it will be again clockwise, so positive. Next we have 30 kilonewton force, and it will have an anti-clockwise, so negative, minus 30 into 2. So this will be approximately 49 kilonewton meter. Next is moment at D, right? So one way of solving moment at D is that we keep going in the same direction. Okay, so I will solve it that way. I will take the section here at the just left hand side and take all the forces. So plus 27.27 into 2 plus 2 plus 4, 8, minus 30 into 6, minus 40 into 2. So when we solve this, we will get the value approximately. I am not writing the exact value, but approximately we will get it as 41.7 kilonewton meter, right? Another way of solving the same values is that you move from this direction, right? So why I'm pointing it out here, because when I was calculating moment at D, as we keep on moving from left to right, the forces and moments keep on increasing, right? So it will take more time to calculate the moments. So if we want to simplify and do our calculations quickly, so we have to make changes on our own. It is not it is not always that you have to move in this direction. Start moving from E also. So it will save time for calculation of D. So what I'm trying to say is, now instead of making section at left of D, I will make section at the right of D and move from this direction, E towards D. So, and I'm writing here or, so this is a alternate way you can move in, you can use any of the way as per your convenience. So now I'm taking section just at right of D. Okay, so the moment will be, the moment, and we start from E point. So the moment due to this 10 sine 40 at D will be 10 sine 40 into this distance, which is 3 meter, and this moment will be clockwise, right? And but so here we will take the sign to be negative. Why? Because now we are looking at the right hand side of the beam, not the left hand side, because this is the right hand side of this section, this section which we have made on just right of B. So when we are looking at its right hand side, then we know from sign convention that clockwise movement in right hand side are taken negative. So we will apply negative sign. So this is how these sign conventions are used, that depending on whether you are moving from left or right. Okay, so as we are moving in right direction here, so we will use this sign convention. Okay, and another force is 22.5, and also this will also have a negative sign because this will be also clockwise. So minus 22.5 into 1, because it is acting at a distance of 1 meter from B. Right, so these two are the only forces, and when you solve this you will get the same result, minus 41.7 kilonewton meter. So you can either solve by this or you can solve by this, any of the directions you can choose, you will get the same value. There is no harm, you just have to use everything effectively which is easier for you and which you find in which you don't get confused also, so you have to consider that, right? So we are getting these moments. Moment at A and E we have already said that these will be 0. So now we have calculated all the bending moments and all the shear forces. Now we will have to just plot these in our shear force and bending moment diagram. Now to plot the shear force and bending moment diagram, I again made the diagram of the beam, and I have extended these lines so that we can get the exact values beneath these points, right? So I have written here the values which we have calculated of shear force and bending moments in the previous steps. So we will just start plotting now. So shear force at A is positive 27.27. So this line is representing 0 shear force. So values above these will be positive. So here I am writing this is 27.27 upward, in upward direction, so positive. Then at B we have a force of 2.72 and it is negative, so I am plotting it below the line. Then at B, on both the sides left and right we have only same value, so there is only one value here, right? Then we move to C. So C also, at C also we have one value, same 2.72, and on left as well as right of A, we will have the same value, right? Next is D. So at the just left of D we got the value as minus 42.72. So 42.72 minus, and at the same point on right, so this was at the left, and at the side we got positive 28.93. So at below D we got two values, one is 42.72 minus and positive 28, so 28.93, right? And at E the value is 6.43. So this is all the values, these are all the values. Now you just have to join them with the help of line or curve. So we will start, so you will start from the direction you have either moving from this side or this side. Okay, so I am moving from A to E because I have solved the question in this direction only. So first is 27.27 at A, then at B we have minus 2.72. So as I have told you, when we have a concentrated load and we want to join the shear force values, so we have to use straight line for that. So in this way we will use the straight line. And between B and C also there is only concentrated load, so again straight line, and also we have the same values here. Then between C and D, so we will go from C to D. So D has two values, 42.72 and 28.93. So first you will go to 47. You will not join 2.72 with 28.93. You will join it with, you will join it with the um, this 42.72 because we are moving in this direction. So first we are moving from A to E, so we will first take left side then right side. So at the left side we are getting 42.72, and as this is UDL between C and D, so we will join these with the help of a inclined line. Okay, 42.72, right? Then at D only we had another value. So from 42.72 minus 42.72, the shear force changed to 28.93 at just right. Okay, and at E we have this is a UVL. So for UVL, while we are drawing the shear force diagram, we use parabolic curve. So this will be somewhat curved. So we can write it, this is parabolic and this is inclined. So this is the shear force diagram. So these are positive values and these are negative. Now so this was shear force. I will mention here that this is a shear force diagram. Now I am plotting the bending moment diagram. So now we will look at these values. So moment at A was 0, at B it was positive 54.54. So I will draw it below B, 54.44. At C it was 49, approximately 49. At D it was minus 41.76, so below the line, and at E it was 0, right? So now we will join these. So as between A to B we have only point load which is 30 kN, so we will join it with the help of a inclined line, right? Then between B and C also inclined line. Then from C to D we have uh, a UDL. So for when we are drawing the bending moment diagram and joining the bending moment values, then for UDL we have to use parabolic shape. So we will join it like this, somewhat like this, right? And then from D to E, because we have now we are now in D position. So from D to point E we have a UVL. So we will join these with the help of a cubic curve, because for a UVL the equation for bending moment is cubic in equation. So this is cubic. So we can mention it here for our understanding that this is cubic curve and this is parabolic in shape, and this is inclined. Always use scale for inclined and straight lines and use free hand for parabolic curve. So this is the bending moment diagram and the shear force diagram for this beam. Okay, these are positive and these are negative values.